Hello everyone, and once again welcome back to the Chem School. Today we are going to start with a very important topic in organic chemistry, or you can say chemistry, and that is hydrogen bonding. Okay, so we will talk about most of the examples in organic chemistry. We will take few examples in inorganic chemistry as well. So let's get started. So now let's focus on what are the main conditions for hydrogen bonding. Okay, and these are the most important ones. Now the first thing is you should have an electronegative atom, and that electronegative atom is usually NOF, that is nitrogen, oxygen and fluorine. Okay, so electronegative atom, NOF, nitrogen, oxygen and fluorine, and they should have H directly attached to them. Okay, it means, example I'll just take, let's say you talk about water, H2O. So you know that in water oxygen has 2 hydrogen attached to it. Similarly, you can talk about ammonia, NH3, HF, alcohol, and so on. The list can go on. Okay, so in this case, what is happening? First, we said you should have electronegative atom. Check, everyone has electronegative atom, that is oxygen, nitrogen, fluorine, again oxygen, and all of them have at least one H directly attached to them. Correct? In case of water, you can see you have 2 H. In case of alcohol, at least you have 1 H, but you should have 1 H directly attached. That is very important and mandatory. Okay, the next thing, the electronegative atom that you're talking about, that is NOF, nitrogen, oxygen and fluorine, they must be nucleophilic. Most of the time students miss this concept and lose marks on this. Okay, now what do I mean to say? Just understand. Let's say I say you have water. In this case, your oxygen is having a plus charge. In water, oxygen has 1 lone pair, but this oxygen is having 1 plus charge. Okay, so in this case, it will not show hydrogen bonding. This is again very important. Okay, similarly, if you have alcohol, oxygen with a plus charge, again this will not show hydrogen bonding. Why? Because this oxygen is now electrophilic. Correct? So remember that the electronegative atom that we are talking about, that is NOF, it must be nucleophilic. This is a very, very important condition. Clear? Okay. Next thing, the atom that we are talking about, that is electronegative atom, it must be smaller in size. The smaller the size, the more will be the hydrogen bonding. Okay, that is the reason why it is important. So stronger hydrogen bond will always come from the smallest atom, right? And we know that if the atom is going to be smaller, then the electronegativity is definitely going to be higher. Correct? Now what happens? When you have this strong hydrogen bonding, the overall energy of the system keeps on decreasing. And when the energy decreases, we all know that they are inversely proportional to each other, that is energy and stability. So if the overall energy of the system is less, the stability of the system is going to be very, very high. Okay, so again conclude, I repeat, you should have electronegative atom, that is NOF, nitrogen, oxygen and fluorine. Okay, the next thing, this electronegative atom must have H directly attached to them. Okay, this electronegative atom must be nucleophilic. It means it should not bear a positive charge. Okay, the next thing, this atom should be smaller in size. Okay, so if you talk about nitrogen, oxygen and fluorine, we know that fluorine has a smaller size, so it will show higher hydrogen bonding. Clear? So smaller the size, more will be the electronegativity and stronger will be the hydrogen bonding. And stronger the hydrogen bonding, the energy of the system is going to be less and the stability is going to be more. Okay, there are few things in chemistry. We know that chemistry does not exist without exception. So there are some cases where chlorine also shows hydrogen bonding, and some examples where carbon shows hydrogen bonding. So we will just remember, like carbon and chlorine can also show hydrogen bonding, but that is exception and we'll take it at the end. Okay, so that should not be a problem. So the next thing that we should understand is what are the different types of hydrogen bond. Clear? So there are usually 2 different types of hydrogen bond, and that is you have an intermolecular hydrogen bond and you have an intramolecular hydrogen bond. Now what is the difference? In intermolecular, see, whenever you say that you have an intercollegiate festival, it means between 2 different college. But when you say it is an intra-college festival, it means it is within the same college. So that is the same difference that we are talking about here. Okay, so when you have 2 neighbors interacting with each other, or 2 or more molecules interacting with each other, then it is called as intermolecular hydrogen bond, or it is called as intermolecular forces. Okay, so I repeat, intermolecular hydrogen bond is going to be with neighboring molecules. Okay. And when you talk about intramolecular, that is going to be within the same molecule. This bond will exist within the same molecule. It means you have nothing to do with your neighbor. Clear? Fine. So I repeat, it is within the same molecule. And this is a common term that you will listen in chemistry. So in chemistry, whenever you say intermolecular forces, it means intermolecular, it means with the neighbors. And whenever you say intramolecular, it means it has to be within the same molecule. Clear? Fine. Next thing. Now let's talk about intermolecular force and let's see where is the hydrogen bond in that case. And let's confirm all the cases. So you can see I have taken water. You know that oxygen has lone pair, so it is nucleophilic. The electronegative atom is having H attached to it. Clear? And usually the electronegative atom will have the electronegativity which is greater than or equal to 3. And we know that in this category, the best one that fits is NOF, nitrogen, oxygen, fluorine, and you also have chlorine. Clear? So usually the electronegative atom should have electronegativity greater than or equal to 3. Most of the time this is the case. Clear? Now, let's draw the intermolecular hydrogen bonding. Now what will happen? This oxygen is having lone pair. This will behave as a donor to the neighboring hydrogen. Why? This hydrogen electron has been pulled by this oxygen. Therefore, this hydrogen will have delta positive charge. And this oxygen will have delta negative charge. Right? And we now know that they are opposite charges and therefore they will attract each other. Fine. So, in this case, what is happening? This oxygen will form a weak bond with this hydrogen. And this bond is called as hydrogen bonding. Clear? So, when a donor is going to pull another electropositive hydrogen towards itself, then you say that this is hydrogen bonding. Where else can we have hydrogen bonding? Let's draw that. So similarly, this oxygen is the donor and this hydrogen can have hydrogen bonding. Okay, this oxygen is the donor and this hydrogen can have hydrogen bonding. Okay, similarly, this will extend as a network in water molecule. Fine. So because these are between two different water molecules, therefore it is called as intermolecular hydrogen bonding. So this is the intermolecular hydrogen bond. Okay. Have a look at the next one. In this case, what is happening? Now I have drawn a structure which is called as salicylaldehyde. And this salicylaldehyde have one OH group and has one aldehyde group. Okay. So what is happening? You have this H which is the acceptor and you have this oxygen which is the donor. So in this case, what is happening? This hydrogen will come in contact with this oxygen. So this oxygen is now getting attached to this particular hydrogen. So this is again hydrogen bond, but because it is in the same molecule, it is going to be intramolecular hydrogen bond. Okay. The next thing that you should know about hydrogen bonding is, I hope this is very clear. Clear? Okay. The next thing that you should know about hydrogen bond is they are stronger bonds. Okay. But they are not stronger than your ionic or the covalent bond. Fine. They are definitely more stronger than your van der Waals bonds. That is when you talk about dipole-dipole interaction, ion-dipole interaction. Okay. So when you talk about the energy wise, van der Waals are going to be the weakest. Okay. So van der Waals forces are weakest, followed by H bond will be stronger. Okay. Then you will have your ionic and covalent. That is the strongest. Why? Because the energy that is required to break this bond differs, and it differs vastly. Now let's talk about that. When you talk about ionic or covalent bond, they will usually have a bond energy that is greater than 200 kilojoules per mole. Clear? Similarly, when you talk about H bond, the bond energy lies somewhere between 8 to 42 kilojoules per mole. And van der Waals force, they have usually approx around 8 kilojoules per mole. Clear? So now we understand that the van der Waals forces are weaker. Hydrogen bond is comparatively much stronger because of the range. Okay, and ionic and covalent bond, definitely it is going to be much more stronger than your hydrogen bond and van der Waals forces, because these are just forces of attraction. They are not proper bonds. Okay, but when you talk about the bond between O and H, this is a proper bond. Clear? Fine. They are not forces of attraction. Therefore, the energy required to break this bond is going to be much higher compared to this forces of attraction. right? So this is a thing that you should always remember. So now let's solve some example and find out which one will show hydrogen bonding and which one won't, okay? So here there are 5 examples and you need to predict where you will find hydrogen bonding, okay? So just remember all the conditions that we have spoken about, okay? So have a look at the first one. So you know that this is oxygen with 2 CH3. So we know that this hydrogen belongs to carbon. It does not belong to oxygen. It means you have electronegative atom. It is nucleophilic, but it is failing in one condition. It does not have H directly attached to it, okay? So in this case, there will be no hydrogen bonding, clear? So this one is gone. The next one. In this case, you have oxygen with 1 CH3, that does not matter, but this oxygen has one H attached to it, right? So because this is nucleophilic, it is electronegative and it has one H attached to it, it means it will show hydrogen bonding. So the one that I'm going to circle is going to show hydrogen bonding, okay? So we'll just keep it a bit cleaner, fine? So let's talk about the next one. Here you can see NOF, we said NOF with H should have hydrogen bonding. Clear? I repeat, NOF with H and it should not have a positive charge. It is that simple, okay? So you have N with H and lone pair, fine. So this will show hydrogen bonding. In this case, N has 3 different alkyl group. It does not have any H attached to it. It means it will not show hydrogen bonding. Have a look at the next one. HF. So NOF F has H and it will show hydrogen bonding. But in this case, nitrogen has H, it is electronegative, but in this case, what is the problem? It is now electrophilic, it is not nucleophilic. Therefore, this will not show hydrogen bonding. Here only HF will show hydrogen bonding. Have a look at the next example. You have oxygen with a negative charge, so it is very nucleophilic right now. And oxygen is also having H attached to it. It means it will show hydrogen bonding. Clear? At least one H should be present. So F minus. There is no H, therefore no hydrogen bonding. Remember, hydrogen bonding means H should be there. In this case, you have H2S. Sulfur does not show hydrogen bonding, fine? So you need not worry about that. Next, hydrazine. So NH2, NH2. When there is no charge mentioned over here, you should remember that they have lone pair. So this is hydrazine. I'll just write down the name. This is hydrazine, okay? And this will show hydrogen bonding. The next one is H2O2. So sometime it happens that you have to draw the Lewis structure if you're not very sure. So we'll draw for H2O2, fine? So for H2O2, what will happen? You will have oxygen, okay? You have H, right? And your oxygen has 2 lone pairs. So in this case, you can see very clearly that oxygen have H attached to it, right? Therefore, this will show hydrogen bonding. So this is hydrogen peroxide and hydrogen peroxide shows hydrogen bonding. The next one is PH3 phosphine. In case of phosphorus, we didn't say that it is going to show hydrogen bonding. So there is no hydrogen bonding in this case. Carbon is having H. Carbon is not very electronegative. So this will not show hydrogen bonding. There is only one exception. We'll talk about that later. As of now, you need not worry about anything else. So I hope you can predict which molecule is going to exhibit hydrogen bonding. Now let's talk about hydrogen bonding in detail, in depth, okay? Now you will find many questions based on the boiling point when you solve hydrogen bonding. So one of the important one is this, okay? So I have given you 4 examples in which you can find like this is group, this is hydrides. We usually call them hydride families, okay? So hydride of group 17, 16, group 15 and group 14, okay? So now let's solve each of them. Remember, whenever you talk about boiling point, the most important factor that talks about boiling point is the intermolecular forces. The stronger the intermolecular forces, higher is going to be the boiling point, okay? And that is what we need to see over here. Which one is going to have higher intermolecular forces? Usually what happens, the molecule with higher molecular weight will have stronger intermolecular forces. Why? Because it is heavy, it is going to settle faster, okay? There are many other factors, but let's keep that in mind. So the molecular weight should be more if you want the boiling point to be high. The second thing is the intermolecular forces should be strong, okay? So have a look at this example. So you have HF, HCl, HBr, HI. You know that you're going from top to bottom in the periodic table. So the mass is increasing. So HI will have the highest mass over here, okay? So based on that, HI should have the highest boiling point, right? But there's a problem over here. The intermolecular forces of HI is weak. compared to HF. Why? Because we know one very important thing, that HF shows hydrogen bonding, and hydrogen bonding is very, very strong. This is going to have van der Waals forces of attraction, while this is going to have hydrogen bonding. Clear? I repeat, HCl, HBr, HI, they will have van der Waals forces of attraction, while HF is going to have something called as hydrogen bonding, and therefore the boiling point trend will be HF will have the highest boiling point, followed by obviously HI. Now you will go as per the mass, okay? So HI, then HBr, and the least mass will go to HCl. Clear? Similarly, have a look at the next one. It's the exact same concept which is applied over here. The mass is increasing from top to bottom in the periodic table to H2Te, that is tellurium hydride. This is going to have the highest mass, but this has van der Waals forces and this has hydrogen bonding. So H2O is going to have unexpected high boiling point. Okay, so H2O followed by H2Te, followed by you will have hydride of selenium, followed by hydrogen sulfide. Clear? Next one, the same thing. This is having hydrogen bonding and others will have only van der Waals forces, and therefore you have ammonia with the highest boiling point, followed by LBH3, followed by arsenic hydride, and followed by phosphine. Is this clear? Have a look at the next one. In this case, you have carbon, silicon, germanium, and tin hydrides, right? The thing is, here carbon does not show any hydrogen bonding, and therefore you will only decide based on the van der Waals forces. So van der Waals force is going to be highest for this one. Therefore, that is going to have the highest boiling point. So for the last one, the trend will be this. And then methane. Clear? So you can see the difference. Wherever you have hydrogen bonding, they have the higher boiling point. Where you don't have the hydrogen bonding, the boiling point will increase from top to bottom. That is when you talk about P block hydrides. So I hope this is very, very clear to all of you. So now let's talk about one more very important detail of hydrogen bonding, and that is solubility. Right? Here I have taken two examples. That is, you have a sodium cation and you have ammonia. Okay? We need to find out which one of them is going to be more soluble in water. So when you talk about Na cation, when it goes in water, what happens is the water has two charges. That is, oxygen is going to behave as a negative charge and hydrogen is going to behave as positive charge. So water is a dipole molecule. It is a dipolar molecule. So in this case, what happens? Every oxygen will align itself towards Na plus, that is cation. Okay, so what you have is the cation is now surrounded by dipole, and therefore this is called as ion dipole interaction, and we should know that ion dipole interaction is a type of van der Waals force. So in this case, what is happening? Water and cation is showing van der Waals forces of attraction. Okay, but in the next one, if you talk about, that is ammonia, we know that this is NOF, that is nitrogen, right? And this can show hydrogen bonding. When it goes in water, water is again having oxygen, it again shows hydrogen bonding. So what will happen? So now the H here and this oxygen will have intermolecular hydrogen bonding. And when you talk about energy, in this case, more energy will be released, more stability will be assigned to the system. And that is the reason this bonding will take place at a much higher concentration. And when the concentration is high, the solubility is going to be more. Fine. So always remember, in this case, what is going to happen? Because there is hydrogen bonding, intermolecular hydrogen bonding, this is going to be more soluble in water than your compound which are having van der Waals forces of attraction. Based on a similar thing, you can solve one more example. That is, try to find out, like, from carboxylic acid, okay, and alcohol, okay, and you can take, let's say, RNH2, that is primary amine. Which one is going to be more soluble? So you can take this as homework. Clear? So I hope you will work this out. So let's talk about some more examples that are important with respect to hydrogen bonding. Okay, so now in this case, what is happening? We have taken two molecules, that is H3BO3 and RCOOH, that is carboxylic acid. What happened in this case is that in nature, most of the time when you talk about their molecular weight, they are found as dimers. Okay, dimers means if you talk about the molecular weight, you will get the molecular weight as double. Why this is happening? Now when you talk about H3BO3, what is happening is each boron will be surrounded by 3 OH, trigonal planar geometry. So what is happening is this oxygen is going to form hydrogen bonding with the adjacent hydrogen, right? Similarly, in this case, you will have hydrogen bonding. So because of hydrogen bonding, what is happening is this two molecules will stay together, and that is the reason if you get the molecular weight as double, you will say it is dimer. Okay, so if 3 molecules come together, you will say it is trimer. If n number of molecules come together, you will say it is polymer. Fine. So in this case, because of hydrogen bonding, usually H3BO3 exists as a dimer. Okay, it is only when you heat it at a very high temperature they are going to separate. Clear? Similar thing happens with most of the carboxylic acid, not all, right? So most of the carboxylic acid, what happens is, again, this carbonyl oxygen, in this case, what is going to happen? You will have hydrogen bonding with this OH. Similarly, this OH ka H will have hydrogen bonding with this oxygen. Clear? So again, in this case, carboxylic acid is existing as dimer. It means the molecular weight will appear to be double compared to the usual ones. Okay. So remember, because of hydrogen bonding, some molecule can exist as dimer, trimer, and so on. So initially, if you remember, we said that hydrogen bonding can be seen in carbon and chlorine as well. Okay. So I'm taking these two examples which are very well known. Okay. So have a look at the first one. What is happening is, when you mix chloroform and acetone, what actually happens is, in chloroform, we know that this carbon is now highly electron deficient. Why? Because it is attached to 3 different chlorines. So what happens is, this chlorine will start pulling electron towards themselves. So when the chlorine pulls electron towards themselves, the carbon has to compensate that electron. So what will carbon do? It will start pulling electron from hydrogen. Usually what happens, the electron in carbon and hydrogen is equally shared. But now what is happening? Carbon is pulling the electron towards itself. So when carbon is pulling the electrons strongly towards itself, you will have a charge develop on that. So in this case, the carbon will have a partial negative charge. So we know that because it is having a partial negative charge, now it is behaving as electronegative. Okay, the electronegativity is not 3, but still it is sufficiently electronegative, while this hydrogen is now behaving as partial positive. So what will happen? When you have acetone, the carbonyl here, what will happen is, the oxygen will start pulling the hydrogen towards itself. The oxygen will start donating electron to this electron deficient hydrogen. It will behave as a donor. So now you know that if oxygen is donating electron to the hydrogen, now in this case, the bonding between them is going to be hydrogen bonding. Okay. So this is when the carbon, it is not NOF, nitrogen, oxygen, fluorine. This is not the case. It is in carbon. Okay. In this case, carbon is also showing something called as hydrogen bonding. I hope this example is very clear. Compared to this is less known, but this one is very, very famous. Now there's a molecule called as chloral. So what is chloral? You have CCl3. I'll change the pen. You have CCl3, okay, and at this site you have aldehyde, CHO. So to aldehyde, if you add water, then you get this structure which is called as chloral hydrate. So in chloral hydrate, what happens? This usually on one carbon, 2 OH is unstable. We know that geminal diols are unstable, right? I repeat, if on one carbon you have 2 different functional group, it is called as geminal. And if you have 2 OH on the same carbon, it is called as geminal diol, and they are highly unstable. But this is an exception, that is chloral hydrate. In spite of being a geminal diol, it is highly stable. Why? Because in this case, what happens is, the chlorine and hydrogen will have an unusual bonding, and this is called as hydrogen bonding. In this case, this hydrogen bonding is intramolecular H bond. It is within the same molecule. Okay, it is because of this dehydrolysis will not take place. Usually what happens, if you have a carbon with 2 OH, elimination of water takes place and you will get this structure. Okay, and usually people say that this reaction is going to be reversible, but in this case this does not happen. In this case, if you add water to chloral, you will get this, and this is going to be very, very stable. Why? Because of this intramolecular hydrogen bonding. Okay, in this case the hydrogen bonding is between 2 different molecules, so you know that this is intermolecular H bond. So remember these 2 examples which are very, very important. Even if you don't remember, this is fine, but this one you have to remember. This is very, very important example. Now students, when you come to hydrogen bonding, especially hydrogen bonding in water is very, very important, and there are a few important points that we should remember. The first one is, When you talk about something called a mole concept, most of the time you will come across this question. Like they say that one molecule of water forms 4 hydrogen bonds. So 1 mole will form how much, and so on. So for that we will just remember this, okay? Now usually what happens, if you have 1 molecule of water, 1 molecule, so oxygen will have 2 lone pair. So this 2 lone pair, okay, this 2 lone pair, each of them will have 1 hydrogen attracted towards them. Okay, so 2 lone pair will have 2 hydrogen attracted towards themselves, and on the other side you have 2H. So the 2H will get attracted to 2 different oxygen, right? So what will happen, and that is the reason 2 lone pair pulls 2 hydrogen, right? And 2H is now moving towards other 2 oxygen, and that is the reason you will have 4 hydrogen bonding in 1 water molecule. So you can just remember this as a fact, okay? The next one is ice floats on water. So you have studied it for a very long time and you should know the reason for this. Why? So the reason is, we know that the density of ice is less than density of water. Okay, usually the density for ice is in solid state. Solids are usually heavier. Okay, but in this case it is the reverse one. That is, liquid is heavier than the solid. Why? Because the density here, if you say this is 0.9 grams per cm cube or per ml, you can say, and here the density is, we know that it is 1 gram per cm cube. Okay, why? Okay, what happens is when hydrogen bonding takes place, okay, at 0 degrees Celsius, you get ice, and at this time what happens is, when the hydrogen bonding is forming, you will have a cage-like structure. That is, in between you will have a lot of vacant or empty space called as void. Okay, now what happens? We know sponge is very light. Why sponge is very light? Because it has a lot of empty space which has air in that. Okay, the same thing is with ice. Okay, ice has a lot of empty space in that which has a lot of air in that. Okay, that is the reason ice is going to be much lighter. When you talk about water, water is free to move. So what happens is, because of strong intermolecular forces, all the water molecules are now going to bind to each other. Okay, and that is the reason the density is going to be more, because the void space is less. Air is going to be released. Okay, so this is the scientific or the chemistry reason, you can say. That is, because of the larger void present in ice, it is less dense and therefore it floats on water. Clear? I hope with respect to chemistry it is very clear to you. So now let's talk about the last part of hydrogen bonding, and that is intermolecular hydrogen bonding. So I have taken 2 very important examples, and that is orthonitrophenol and paranitrophenol. So in aromatic ring, if you have 2, or in benzene ring, if you have 2 groups adjacent to each other, we know that it is called as ortho. And if they are parallel to each other, then you will say it is para. Clear? So now let's talk about which hydrogen bonding is present in both of them. Okay, so have a look at the first one. In this case, you can see that you have OH and here you have nitro. So N has double bond O. So this O will donate electron to this H, right? Now this is one molecule, and in one molecule you have hydrogen bonding, and we know that in the same molecule the hydrogen bonding that is present is called as, intramolecular hydrogen bond. Clear? The next thing that you should remember is, whenever you have this intramolecular hydrogen bond, so hydrogen bonding is present within the same molecule. So which type of bond it will exist with the neighbor? That is, if you have 2 orthonitrophenol, what is the force of attraction acting between them? Okay, so now the force of attraction between them is going to be something called as van der Waals force. So 2 orthonitrophenol will have van der Waals forces amongst themselves, but within the same molecule they will have hydrogen bonding. Clear? So I repeat, they have van der Waals forces with neighboring molecule, or you can say with neighbor. Okay, but have a look at the next one. In this case, what is happening? The OH and the nitro are very far away from each other. That is the reason they cannot have hydrogen bonding within the same molecule. So what will happen now? This OH will interact with the nitro of the neighboring paranitrophenol. Okay, I hope you get it. I repeat, what will happen? This will now interact with the nitro, okay, of the neighboring paranitro group. Okay, similarly, this oxygen will interact with the neighboring OH or hydrogen of the paranitrophenol. So you can see that this is a different molecule and this is a different molecule. So two different molecules are having hydrogen bonding. Two different molecules are having hydrogen bonding. So we know that this is going to be intermolecular H bond. Clear? So within neighboring molecules you have intermolecular H bond, while in this case with neighboring molecule you have van der Waals forces of attraction. So which one is going to be stronger, right? Definitely we know that this one is going to be stronger because this is H bonding, right? That is the reason that the boiling point of this compound is going to be more. Okay, so whenever you have this para effect, in this case what will happen, the boiling point of this type, the one which has intermolecular bond, H bond, hydrogen bond, will be more compared to this one. Okay, so the boiling point of this molecule is going to be less. So because they have different boiling point and they are liquids, okay, how will you purify them? The best method for this is a process called as fractional distillation. Clear? So similarly, when you have two ortho OH groups and para OH group, similarly you can purify them with something called as fractional distillation. Okay, so this is the very most important part when you talk about organic chemistry, so you should remember this. Okay, this was all for the day. See you soon in the next class. Thank you.